associated with three details: TAD, port number, IP address. Port number is kind of fixed. TAD and IP address. TAD recognizing the traffic belongs to which subscriber. There can be 500 TADs. But IP address is the node's IP address, which could be, for example, GNode B's IP address, in case if it is the GNode B that is creating this tunnel endpoint. But if node 1 created this tunnel endpoint, this tunnel can be only used to receive the traffic for the incoming traffic. You cannot use this tunnel ID for sending out the traffic. So that means somehow node 1 created this tunnel, TAD, port number and IP address things. It kind of somehow provides these details to node 2, tell the node 2 that, hey, if at all you want to send the traffic related to any particular subscriber, you please send the traffic to me by using this TAD in the GTPU header. You please put this TAD in the GTPU header field so that I will recognize that this IP packet belongs to which subscriber. And you send the traffic to me on this IP address. This is my IP address. It kind of provides these details. Node 1 will provide it to node 2 before even sending the first packet, before arriving even the first packet. Actually, this information, this tunnel information would be exchanged by using control protocols, control plane protocols like PFCP, NGAP, XNAP, etc. The control plane protocols will exchange these tunnel ID related information. GTPU is not capable of exchanging it on its own, these tunnel IDs that are getting created for the subscribers. So GTPU is a user plane protocol to carry the IP packets inside its body. But for carrying those IP packets, it needs to create these tunnel IDs. But exchanging the tunnel ID information cannot be done by the GTPU on its own. Instead, it will have to use the services of some other control plane protocols, like XNAP, for example, or NGAP, or PFCP. Once these protocols will somehow carry the information to the other node, then only the other node, by using these details, it can send the traffic to this node for that particular subscriber for whom this TAD is created. But now in this case, only node 2 can send the traffic to node 1 for a particular subscriber. But what about if node 1 wanted to send the traffic to node 2 in the reverse direction? For that, you require one more tunnel endpoint, again, which is also a combination of TAD plus port number and IP address. And once the tunnel ID is created, again, the tunnel can be used for receiving. Now, this tunnel ID is created by node 2 before the actual data is sent by node 1. By using the signaling protocols, this information would be sent to node 1 beforehand. So node 1, by using that information, by using the tunnel details, it can pack the data into GTPU protocols and can dispatch it to node 2. So node 2 recognizes that this data belongs to which user based on the TAD used in the header, in the GTPU header. Now, both these things together, we call it as a tunnel. A tunnel can be two directional, like you can send uplink traffic, downlink traffic. For example, if you take these nodes, this node has GNode B, this node has UPF. So GNode B created one tunnel ID for subscriber with its own IP address. It's pointing to its IP address. UPF created one tunnel ID for the subscriber with its own IP address pointing to its IP address. Now, each other, they somehow exchanged this information. If GNode B need to send uplink traffic, it will pack the uplink traffic into GTPU packet, IP packet into GTPU packet. In the GTPU, it will have to use this tunnel ID as the reference so that UPF can recognize that, okay, this traffic belongs to so-and-so subscriber. Because with the help of that created tunnel ID, you recognize that user because you are creating one tunnel ID for one subscriber. So that is how the logic works. In case of downlink traffic, it is the opposite. If UPF is sending the downlink traffic to GNode B in the downlink direction, in the header, GTPU header, UPF need to attach the tunnel ID provided to him by GNodeB in the GTPU header. And when it is received by GTPU, because IP address is used as GNodeB's IP address, once it is received, GNodeB understands that, okay, I only have created this tunnel ID that belongs to so-and-so subscriber. Now I can detect that this traffic belongs to so-and-so user. Even if I have 500 subscribers for whom I am receiving the traffic on 500 different tunnel IDs, I can segregate each user's traffic. I could do that. Because each subscriber has got a different TAID. 500 subscribers, 500 tunnels. Each tunnel has got 2 endpoints on either side of it. So what data can be carried on GTPU? GTPU travels on UDP IP L2L1, but inside GTPU, you can pack a TPDU. The TPDU can be IP packet, or I talked about private private 5G networks. In that case, they can be Ethernet PDUs, or sometimes unstructured data, which is not predefined into any particular protocol format. Even that is allowed in 5G. But we are ignoring these two cases. These are for advanced 5G scenarios, which is not part of our curriculum. So Ethernet PDU and unstructured data PDU is absent. So we consider IP datagram. IP datagram is known as TPDU, and it is packed in when it is packed into GTPU along with the GTPU header. Together with this TPDU, which is nothing but an IP packet that belongs to the mobile, we call this as GPDU, which is GTPU PDU, prepared by GTP protocol, which is containing a TPDU inside or IP datagram inside. Now, at GTPU level, you attach TAD that is negotiated with the signaling protocols. IP address of the GTPU nodes who are exchanging the traffic, source node and destination node. It could be GNodeB, UPF, or GNodeB, etc. Port number is kind of fixed, mostly fixed to 2152 whenever you are sending GTPU traffic in either direction. So at 3 layers, 3 details. At application level, TAD. At transport level, port number. At IP level, we have address. Why port number is fixed? You can ask. Typically, for any famous application, port numbers would be fixed. For example, if you take HTTP, port number is 80. If you take FTP, port number is 2021. Like that, for any famous protocol, port numbers are reserved by IETF. Similarly, there is a port number that is reserved for GTPU. That is 2152. That's why kind of that is used always. 2152 is used as the port number to recognize that the data we are packing into UDP is GTPU data. Because you have to always note down what is the higher layer data that you are packing inside. Now, that is GPDU, carrying the high IP packet packed inside. But sometimes the GTP message that you are sending may not carry any higher layer data or IP packet. Sometimes some GTPU information can be sent alone for some special purposes. Like, for example, something called as path management messages or something called as a tunnel management purposes. We use these messages without containing the TPDU, without packing the higher layer data IP packet inside it. It is like GTPU related control information. It goes from GTPU to GTPU. Inside it, nothing would be present. It is the some kind of information GTPU would like to send to the other GTPU. So it contains something called as IEs, information elements, which are nothing but parameters. A fancy name for parameters is called as IEs. I have told you this earlier as well. When we have a GTPU packet prepared like this without containing IP packet inside, such a thing is called as a signaling message. When we are sending a signaling message, TAD will be set to 0, representing that this message doesn't belong to any particular subscriber. It is general GTPU specific data. Port number is fixed to 2152 and IP address will be pinpointing to the source and destination IP address of the components who are exchanging this GTPU traffic. Those rules are the same. But only difference is TAD is set to 0 here in these cases. Because it doesn't belong to any particular subscriber, as it is not packing any IP packet inside. It is like, if you remember our radio protocol stack, I told you that every protocol can exchange some control information. Similar to that, GTPU can also send some signaling information with each other. To do that, they use this. That time they set the TAD to 0, representing that it's a general message, doesn't belong to any particular subscriber. And inside it, there is no IP packet present. Okay, now we have to see what is this GTPU header first of all. So this is the GTPU header that would be present when we are packing a GTPU message. I will explain these fields and what are their purposes one by one. First, version. The value always will be set to 1. It is a 3-bit field. The value will be set to 001, which represents version 1. Because the GTP protocol software version we are learning is version 1. Binary, decimal value is 1, but when it converted into binary, it need to occupy 3 bits length, fixed size, 001. 2 most significant bits would be set to 0, least significant bit is set to 1. So ultimately the value, decimal value out of it is 1. When you convert that binary thing to decimal. Next. PT, protocol type. We ignore this protocol type, but whenever it is a GTPU packet, its value would be set to 1. When it is set to 0, what is the meaning of GTP prime, GTP version 1C? All those things we won't study right now. This is part of GPRS and required only in 2G, 2.5G and 3G, not needed now. So it won't be used in 5G network. So we are ignoring, we never set the value to 0. So protocol type field value always will be set to 1 in 5G scenarios. In either 4G or 5G scenarios, it is always set to 1. Which represents that the packet we are studying is a GTPU packet. GTPU version 1 user plane, not control plane. Okay, next. Next bit is just dummy. It will always be filled with 0. Ignored. Next 3 bits, each bit is 1 bit here. Next 3 bits will represent whether particular field is significant or not. If the E bit is set to 1, this field is important. This next extension header type is important. When S bit is set to 1, this sequence number is important. Sequence number field is important. When PN bit is set to 1, then this NPDU number is important. Otherwise, these are ignorable. So when these fields are set to zeros, so the receiving entity will know that in the GTPU header, all these fields are ignorable. You can throw whatever the values you have received into dustbin. You don't care about them. That is the meaning of it. But out of this sequence number, this NPDU number is actually not used in 5G operations. LTE or 5G, it won't be used. It always will be set to 0. This PN bit. So this NPDU number will always contain zeros. It will be thrown into dustbin. It is used only 2G, 3G scenarios, that to 2G, 3G handover cases. That kind of not needed because they have advanced the technology. That mechanism was not required in LTE. They got rid of it, the requirement. But this protocol continued in all the releases. The same protocol used in different technologies. Okay, next. The sequence number is also mostly set to 0 in case of 5G scenarios, mostly. But in some special cases like echo request, echo response, it can be set to 1. Especially when you are sending something called as signaling messages without carrying any IP packets inside. That time, this sequence number can be set to 1. Or in case of some mechanism called as indirect data forwarding tunnels, which I won't introduce to you because that core network learning part is not included. So in that cases, this bit would be set to 1. What is direct tunnels, what is indirect tunnels, you will learn them later. Right now, not required. Maybe at XN interface, I will talk about it a little bit if time permits. But mostly you can ignore this sequence number also. You are ignoring this, you are ignoring this. Tunnel ID, we know. Tunnel ID is 32 bits or 4 bytes. Each line here represents 8 bits. So 8 bits, 8 bits, 8 bits, 8 bits. So 4 into 8, 32 bits. Tunnel ID. Each mobile equipment will have a separate tunnel ID on the either N3 interface or XN interface, wherever the GPU traffic is being exchanged by carrying the IP packets inside. Now, there are different message types are possible. What are those message types? We see in the next slide. Length will indicate what is the length of the GPU packet, including the IP packet we are packing inside. And the length field size is 16 bits to 8 bits, 16 bits. Maximum possible value is 2 power 16 minus 1. 2 power 16 is 65,536 minus 1 is 65,535. So maximum GPU packet size by packing a IP packet inside is 65,535 bytes. For example, if you have packed an IP packet of size 1500 bytes into it, 1500 plus the header size, together we'll put the value in this length field. For example, if the header is 8 bytes, let us suppose, or 12 bytes, 12 plus IP packet size is 1500. 1512. So here you will represent a value 1512 by converting it into binary values, zeros and ones. You put the value there in this length field position. Now this TID field would be required if it is user specific information. If it is not present, if TID field is not present, then it will be identified on the basis of message type. You can identify whether TID is required or not required. Whenever we are sending GPDUs, which are carrying higher layer data inside, IP packet inside, then definitely TID would be present. TID field is present. But when you are sending some signaling messages, etc., that time TID won't be present. On the basis of message ID, the receiving entity can recognize whether TID is present or not present. So what are the message types we have? Echo request, echo response, error indication, supported extension header notification, tunnel status, end marker, and GPDU. So these are the possible types of GPDUs you can send, or GTPU messages that you can send. And each thing is required for one particular purpose. And we will study them one by one. These messages. What messages are required for what operation? The message length field is 8 bits. The possible values are ranging from 0 to 255, because if any field is 8 bits, the maximum value is 2 power 8 minus 1. 256 minus 1 is 255. So 0 to 255. So you can find the table containing values ranging from 1 to 255. Lot of numbers are reserved for future operations. Only 1, 2, 3, 4, 5, 6, 7 numbers are useful right now in the present generation. In the future, if they require it, they will use those numbers for different purposes. But right now, only you can generate 7 types of GTPU packets. And out of them, one of the packet is your GPDU containing the IP packet or higher layer data inside, whose value is set to 255. 255 means 8 ones. Whenever all the 8 bits are set to 1, value is 255. 128 plus 6 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. So when all the 8 bits of this message type is set to 1, it kind of gives a hint to the receiving entity that hey, this is a TPDU belongs to some subscriber whose tunnel ID definitely will be present from the 5th byte onwards, 5th to 8th byte. Based on it, you will recognize which subscriber's data it is. or which subscriber's IP packet is present inside it. See, after the header, your data would be present. The higher layer information would be present after the header is completed. But anyway, we study these messages and their purposes. I won't go through the deeper details, but I will try to explain them as higher level as possible, because we don't have enough time. First, echo request, echo response. Normally, these messages are used for general purposes called as path management. When there is no traffic going on between two GTPU nodes, they kind of get a doubt with each other. Hey, why the traffic is not going on? Why there is no GTPU packets that are getting exchanged between you and me? Are you dead or what? The one node get a doubt. To verify or to confirm, it sends a echo request to the other node. Hey, man, I'm sending you echo request and setting a timer for myself. I'm expecting you to send a echo response within this timer expiry. If you send a echo response, I believe that you are not dead. Why there is no traffic is because of genuine reasons, like there are no users present who are exchanging the traffic. That is why we are not exchanging the traffic. That is why the traffic is not going on. But for any reason, after you send the echo request and this timer that started is expired, before receiving the echo response, node 1 will come to a conclusion that something happened to node 2. Node 2 is dead, or some bad thing is going on with node 2. It will confirm. So this is to confirm whether the path is live or not. The path between two nodes, two GTPU nodes, is live or not, is working properly or not. That is the purpose of this echo request and echo response messages. These are general messages. Will they carry IP packets inside? No. Normally, when do you see echo request, echo response in the network? Maybe night 2 o'clock, night 12 o'clock, when all the subscribers are sleeping and there is no traffic going on between the GNodeB and UPF for any subscriber. Every now and then they will be exchanging these echo requests. Kind of these are health check messages. We can call it as heartbeats to find out whether the other guy is still live or dead. But in the morning time, when huge amount of traffic is going on related to hundreds and hundreds of subscribers, these nodes will never get the doubt and they never need to exchange these echo request and echo response. Because live traffic is going on, they are dealing with it. They will never get a doubt with each other. So nobody would generate echo request. Now, in the GTPU header, when the message code is set to either 1 or 2, they represent echo request or echo response. That means when this message type field value is 0000001 or 10, two possibilities. When it is 1, it is echo request. When the value is 10, which represents 2, is echo response. If one guy sends a echo request with this message type value set to 1, other guy would respond back with the message type value set to 2. Kind of transaction is completed, for which whatever purpose we have generated the transaction, that is considered to be completed. Next, error indication 26. Okay, I think I will go to that error indication first. In the order, we'll see. You have sent any GTPU PDU from one node to another node by including any wrong details that are not expected in node 2. For example, you are including a wrong tunnel ID. Maybe the tunnel ID that never created in node 2 for any subscriber. Or you are trying to send a traffic to a UDP port number that is not present, that is not operational. Something, or you are trying to send a traffic to an IP address which is not active on the GTP node. If you do any such wrong things with the GTPU PDU that you are sending to node 2, if node 2 realizes that why this bugger is sending traffic to me on tunnel ID that I have never created, or on a port number that I have never told him, or an IP address that is not being used. So in such cases, this node 2 is allowed to send a error indication to node 1 and reporting him that, hey, whatever the IP packet traffic that you are sending, GTP PD you are sending it to a wrong location, or to either to a wrong port number or to a wrong tunnel endpoint or wrong something IP address, whatever it is. It will come and explain you about that situation. But only happens in case of negative scenarios. But we don't need to bother much about why the negative scenarios occur and when these things will take place. When there is something wrong going on in the system, which we will not go into those deeper details, not needed right now, because we are learning them. All these subject we are learning half-cooked subject, not full-fledged, as we are not part of our learning. Should not be core network side, not part of our curriculum. Okay, again, let's go back. So that is error indication part. Next, supported extension header notification. What is it? Now, the standard header is this 12 bytes, 1 to 12. After this, there are some additional extension headers that are possible in GTPU. Extension header, that means header can be extended. Instead of 12 bytes, it can be, for example, 16 bytes or 20 bytes, and additional header fields can be included additionally. Now, to GTPU nodes, when they come up for the first time, normally they will exchange these supported extension headers. Hey, what are the extension headers that you support? I support these extension headers. One guy tell the other guy. So they are kind of notifying each other. These are the extension headers I support. Please tell me what extension headers you support. Once they come to some kind of a common understanding, at the time of sending the GTPU PDUs along with the header, they can send this GTPU header along with these extension headers. But at the starting, they have to come to some kind of a synchronization. They have to come to some kind of common understanding what extension headers they both support with each other. But first of all, what are the different extension headers that are supported? Normally, when this message is sent, if you are sending any message for the first time, when these two nodes have started the transactions originally, when they are coming up for the first time, one guy have sent a message with extension header that are not supported by the node 2. That are not supported in the feature in the software in node 2. Node 2 immediately would send back, hey, you are sending an extension header which I cannot understand or my software cannot understand. So I don't support. I support only these extension headers. It will kind of notify this to the first node. So indirectly, node 2 is telling node 1 that if you are attaching any additional headers, they must be understandable by my software. You please make sure that according to the instruction that I am sending. But what are these extension headers, and why do we need them? So these are the GTPU extension headers that we can use, that we can attach in the GTPU packets. So you can attach PDCP sequence numbers, long PDCP PDU sequence numbers, or normal PDCP PDU sequence number. PDCP sequence number can be 12-bit or 18 bits or even higher. Depending on, so when you are sending a GTPU PDU, to that you can attach a PDCP PDU number you can attach. Why do you need to do that? Yesterday, day before, we have studied PDCP. If you remember, any pending packets or any packets that are received out of order, we studied that source GNodeB would be forwarding them to the target GNodeB during the handover procedure. While sending those pending ones, you can attach in the GTPU header, you can attach this PDU number, PDCP PDU number, so that the receiving entity recognizes that, okay, when I'm sending this data to the mobile, once the mobile arrives, this is the sequence number I'm going to use in the PDCP level. So you are attaching that PDCP sequence numbers basically there. So that information would be included in the form of extension headers. Extension header means extra header. Next, PDU session container. This PDU session container is an extension header that carries PDU session user plane protocol data. The one that we have learned at the starting, it will carry the details, this PDU session container. There are NR RAM container and XW RAM container also, which we'll ignore. RAM container also we'll ignore because this is used in 3G. This NR RAM container is used in dual scenarios, dual protocol stack scenarios. This is also used in dual scenarios. We're ignoring those containers. We are not studying them. We have only studied the PDU user plane container. This is nothing but the QFI ID part that we have learned that is going to be packed in the form of an extension header in GTPU. But whenever these extension headers are present, so they are going to be packaged like this. For example, if it is a PDCP PDU number, the PDCP PDU number will be there, associated as the extension header, extra header, on top of the 12 bytes header, which is already present. If the PDCP PDU number is big, if it is 18 bits, you require it to be big. So you are going to take 8-byte version of it, 8-byte size. You attach. I'm not going into the deeper details of why it is 8 bytes or why it is 4 bytes, the protocol level design related details. We are only studying here what kind of information can be added as extension headers. That's it. So when there is a long PDCP PDU number, we can attach that to the GTPU header, especially when you are carrying pending traffic from one node to another node. Or if it is the PDU session container, the PDU session container can be packed as in the form of extension header, which is nothing but the PDCP PDU the PDU session protocol, session user plane protocol data that we have prepared, which is containing the quality of service class identifier or QoS flow identifier and your QMP details, downlink, timestamp information, etc. That package is packaged in GTPU header in the form of extension header. Why it is designed in the extension header? Because this design was not there in 2G, 3G, or when the GTP protocol is developed. It was implemented later. So that is why they have decided to use this field in extension header. All these extension headers are newly introduced. Some of them are introduced in 4G, some of them are introduced in 5G. It's like that. Extension header means which they did not thought originally that required to be present in the form of headers. For example, in 1996, when GTPU was invented, they never thought that this kind of a QFI model would be used in 5G network because 5G specifications came up in 2020s. So they don't know at that time. So they kind of left out a mechanism where they said that in the future, if additional header fields are needed, they must be added in the form of extension headers. For each extension header, there is kind of a code that would is present. Based on the code, you can recognize it. What is the code? How can you recognize what kind of extension header is added? The codes I already have showed you. So if, for example, if you are attaching PDU session container, the code is 1000101. So if this code 1000101 is present in this header position, here 1000101 in the position of next extension header, and that too this extension bit is set to 1. That time definitely extension header is present. In the extension header, you are going to pack that PDU session details, PDU session user plane protocol data that we have studied earlier. you would pack it. If this extension bit is set to 0, this next extension header type values will be set to all zeros. When it is set to all zeros, then this won't be present. This extension header won't be present. Your header will be finished with 12 bytes only, just 12 bytes. But in our 5G case, it is mandatory. Whenever you are carrying the PDU session information, you are going to attach this PDU session user plane protocol data for the GPDU in the form of extension headers. You will add them. Now, one last thing, GPDU, we already know IP packet is packed into GTPU packet is called as GPDU. But what is this end marker? End marker we already have seen earlier also. It is kind of telling you that it is the last one. After this, we don't have any more. We are reporting that. For example, any node, after sending some number of PDUs, it has itself detected that I have dispatched the last IP packet which I am supposed to send. There are no more IP packets need to be packed into GTPU and sent. It kind of need to indicate to node to that my traffic sending is finished. This is the last packet I am sending. While reporting it, it will send this end marker. The code for this end marker is 254 in the message type value. So if you go back, so in the message type, if the value is 254, that is 1111110, that is equal to 254. Then you are giving a kind of a report to the receiving entity that, hey, the IP packet that I'm sending you right now in this last packet, this is the end of it. After this, I'm not going to send you any more IP packets. You can close your tunnel that you have opened. The tunnel ID you can terminate. I don't care. If you remember the tunnel ID concept, tunnels are always created for the purpose of receiving. So this guy created a tunnel to receive the traffic from the other node. But once this node sends end marker, indirectly it is reporting by using a tunnel ID, it is send a end marker. Indirectly it is reporting to node 1 that, hey, whatever the tunnel ID you have created, on which I am sending the last one, because I am sending you the end marker. Now after this, I am not going to send you anymore. This is the kind of end. So if you remove this tunnel ID for this particular subscriber, I don't feel bad about it. Because with this, the transaction is kind of completed. Normally, this would be done when the user equipment is discontinuing the traffic, or when the user is going into idle mode, when you have to remove the tunnels, or during the handover, already you have dispatched all the pending traffic. There is no more pending traffic. In such kind of cases, whenever you have to report that it is the end of the traffic, you will send this GTPU PDU which contains message type value set to 254, indicating to the other node that you can destroy the tunnel that you have created for my purpose. All right. That is the end of our GTPU, which carries what? After the header, it is going to have the IP datagram, but it will note down that IP datagram belongs to which user in the form of TEID. It notes down. Then the GTPU packet is kept into UDP, UDP is kept into IP, and we implement DSCP at this IP level to provide different quality of service for different QoS flow packets. You might have packed maybe 3 different QoS flow packets in 3 different GTPU PDUs. 3 of them are packed into 3 IP packets. But for each one of these IP packets, you use a different DSCP value, so that even though they are being sent on the same tunnel ID for a subscriber, they can have different quality of service implementation on the N3 interface, N3 network. That is why one tunnel ID is enough to send the data that belongs to one subscriber belongs to different QoS flows also. So I have linked that yesterday's opening point. I have closed it today. Okay. The last protocol that we have to study. So now we understood if an IP packet is received from here, how that is identified to belongs to which QoS flow based on the packet filters, and that corresponding QFI ID will be noted down, and then the IP packet is kept into GTPU with the corresponding tunnel details added in the header for that IP packet. So for that IP packet, QFI is being added, tunnel details are getting added. The tunnel ID created by this node. Then pack it into UDP IP, source IP address is UPF, destination IP address is Gnode B, and send the IP packet by including DSCP information on N3 tunnel. Receive it here, opens and find out this data belongs to which UE based on the tunnel ID. And in that UE, it belongs to which QFI, which QoS flow. That is identified at PDU session level details. It's identified. Then the same information would be transferred to SDP. Now SDP need to add the details. So the last protocol we have to study in this user plane part is SDP. SDP also does the same job as this PDU SUPP. Similar job. Stands for Service Data Adaptation Protocol, SDAP. It is used only for DRBs. There can be multiple SDAP entities, one entity for one PDU session. If mobile is connected to multiple data networks, there will be multiple entities. But one SDAP entity might be dealing with multiple PDCP entities, because when it receives the QoS flows, which QoS flow is mapped onto which data radio bearer, SDAP knows that. SDAP not only will know the data belongs to which QoS flow, but that QoS flow need to be sent on which radio bearer. Once you identify the radio bearer, for every radio bearer, we have one PDCP entity present. So depending on it, you have to dispatch the traffic. For example, you received the traffic for QoS flow 3. You identify that it need to be sent on this radio bearer. You have received the traffic for QoS flow 4. SDAP identified that it must be sent on this PDCP, different radio bearer. So SDAP kind of deals with multiple PDCP entities. So the idea is one or more quality of service flows can be mapped onto one DRB, which is allowed, but kind of applicable only in downlink. In uplink scenario, each quality of service flow must be associated with one DRB. In uplink, because mobile can't deal that kind of a heavy amount of MAC level scheduling mechanisms. So that is why they have decided only one-to-one mapping. In case of uplink, in case of downlink, multiple QoS flows can arrive in one single DRB in downlink. If reflective quality of service is enabled, whatever the DRB mapping that is already in place, that will be omitted, and you have to apply the new mapping that is indicated to you. The new QoS flow ID you have to use. Already, if it is linked with the already one DRB, you have to ignore that. Whenever the reflective quality of service is ordered, but we already learned that reflective quality of service is applicable only for NGBR bearers, not applicable for the GBR bearers. So the duty of the SDAP is to map quality of service flows to the DRBs. Which quality of service flow need to be sent on which DRB? It is either done by the mobile equipment side SDAP or Gnode B side SDAP. Downlink, it is done by Gnode B SDAP. Uplink, it is done by mobile SDAP. So whenever these SDAP entities are present, what do they do? What is their basic functionality? As I told you earlier, these are for one PDU session. That is the applicable rule. Now, if multiple quality of service flows are not mapped onto one DRB, in normal circumstances, for example, one quality of service flow is going on one DRB. For a mobile is having, let us suppose, 4 quality of service flows and it is using 4 data radio bearers. In that case, you actually kind of don't require to add the header. Header is unnecessary. So RRC can configure the SDAP and tell the SDAP that, hey, you don't need to add the header. So when SDAP header is not configured case, without adding the header, you simply have to map which QoS flow need to be sent on which DRB. That's it. If you send it to the corresponding PDCP, the job is enough. On the other side, based on which PDCP you have received the data, you can easily identify the data belongs to which QoS flow because it is one-to-one mapping. So in case of one-to-one mapping scenarios, header is not needed. SDAP header is not needed. But if RRC configured the SDAP header, which is allowed even in case of one-to-one mapping also, but wherever it is configured by RRC that SDAP header is mandatory, then you definitely need to note down the QoS flow ID before when it is sent to the PDCP layer. It will note down that QoS flow number, QoS flow ID, QFI, which we have studied earlier. So on the sending entity, if the SDAP header is configured, adding that QFI ID related details is the duty of SDAP. On the receiving side, detecting that, removing that SDP header, we send it the data to the higher layer on the receiving side. But sometimes, especially for the downlink operation, there is a possibility reflective quality of service can be enabled. When UPF is enabling the reflective quality of service, UPF send these details to G node B sending it to the mobile. When mobile received that reflective quality of service related instructions, it need to identify that, it need to act according to that for the next operation. So it need to start changing the quality of service profile mapping rules for the uplink operation for the DRB from now onwards, because reflective quality of service is getting enabled from now onwards. So it will have to check if the reflective quality of service is being requested or not for any DRB. If requested, it will have to take the corrective action and deal with it. But after detecting it, it will kind of remove the header and send the data to send the QoS flow to the higher layers. Higher layer could be anything, your applications. For example, if you take it as the mobile, if you take it as NGRAM, it would be sent to GTPU, because what you extract is IP packet. IP need to be packed into GTPU and send it towards the UPF. There are no higher layers present in NGRAM. Only in the mobile they would be present if it is downlink. But if the SDAP header is not configured, simply when you receive the data on the DRB, you simply send it to a particular QoS flow. You identify that DRB means which QoS flow if SDAP header is not configured. But configuring the SDAP header is the duty of RRC. RRC kind of decides whether it is needed or not needed. Okay. So what are the jobs that are performed by this SDAP in downlink and in uplink? In uplink at the downlink at the NGRAM, at the uplink at NGRAM. So we are studying the duty of SDAP in the NGRAM component here in this particular picture. First, downlink. SDAPs receive downlink data from the user plane function, UPF, on the NGU interface. You would be receiving that on the GTPU tunnel with a TAD present. With that, you can identify which UE and belongs to which PDU session, because TAD kind of map that. For every subscriber, every PDU session, there is a separate TAD created. There is a separate tunnel ID created at GNodeB. Based on which tunnel ID the traffic arrived, GNodeB can detect it. This data belongs to which UE, which PDU session. And also in the GTPU extension header, in the form of PDU session container that is packed inside GTPU header, you have this QoS flow ID present. You have to extract that QoS flow ID. From the, I'm talking about PDU session user plane protocol header that is packed inside GTPU. These details are provided to by the PDU session user plane protocol. So it kind of get the details, which user, which PDU session, which QoS flow, are the same details in the SDAP header. That is what we have learned even in the previous slides. Same details would be added in the SDAP header before it is sent to the lower layers. Same way in uplink, SDAP receives this information from the lower layers. In that, it will be able to find out the data belongs to which mobile and which PDU session, what quality of service flow. These details are intelligently forwarded to your PDU session user plane protocol. Obviously, the details will be added in the form of PDU session container, and along with the TAD, they would be packed into GTPU and sent towards the UPF. So in the uplink, the header information is already attached by the mobile. When mobile sent it to GNodeB, by GNodeB inspecting the header details, it is identifying the data belongs to which subscriber, which quality of service flow. It is providing that information to this PDU session user plane protocol. Once it prepares the details, it is packed into GTPU extension header. Now IP packet is packed into GTPU packet, then sent to UPF. UPF can recognize this packet belongs to which mobile, which QoS flow ID. If it is excessive traffic, I can drop it. I can drop this packet. That is the idea of the UPF. That is why we are attaching that QoS flow ID there while sending it to UPF for identifying which packets are crossing this maximum size limitations, maximum data rate limitations. So in NGRAN, it is the duty of the GNodeB, nothing but NGRAN, to swap the things. In the downlink, it will get the details in PDU session user plane protocol. It will shift those details to SDAP. In the uplink, it will get the details in SDAP header. It will transfer that information to PDU session container, which would be in turn packed into GTPU. So what are the header fields? How the SDAP header mechanism works. This is how it works. If the SDAP header is not configured by the RRC, simply whatever the data that you get from the higher layer, you simply map it onto the corresponding PDCP and send it without adding any header. Normally, in case of one-to-one mappings, SDAP header can be kind of ignored. Or it is RRC decision basically to enable it or disable it. It is the data PDU that you are carrying from the higher layer. But when the SDAP header is enabled, you are going to have the header. But downlink SDAP header is different, uplink SDAP header is different. What is the difference between downlink and uplink? Downlink. 2 bits are present for the purpose of identifying the reflective quality of service related mechanisms, RDI and RQI. RDI means if the reflective quality of service indication is set to 0 or 1. 0 means no action. You are not getting reflective quality of service information. 1 means you have to store this QoS flow to DRB mapping rule. Now, from now onwards, if this application generates any uplink traffic, the traffic need to be sent with the same QFI ID on which you have received the traffic in the downlink. For example, if you have received the data on the downlink with QFI ID 4, you are going to send the uplink traffic also with the QFI ID 4 from now onwards, if RDI value is set to 1. But if the RQI value is set to 1, which is also related to quality of service indication, you kind of store this quality of service to DRB mapping rule information, you forward it to NAS protocol. I have explained to you earlier also that there is a SAP, service access point, between SDAP and NAS. SDAP go and tell this to NAS layer that, hey, I know that normally you only receive the QoS rules from the from the SMF, but it is a special case. I am receiving the quality of service rules in the user plane protocol. That is nothing but SDAP protocol. I'm receiving it. I'm telling it to you because I advise to tell you about this by setting this RQI bit to 1. So whenever RQI bit is set to 1, this mapping rule information need to be updated in the NAS. It should be informed to NAS protocol software that this particular quality of service flow mapping rules have been updated for uplink traffic of this particular application. Earlier, mobile might be using a separate quality of service flow, but it now need to change it to the new quality of service flow. Nothing but same quality of service flow. It have to use even in uplink by using same quality of service implementation. Next, QFI. QFI is the QoS flow ID. This is the one that is getting shifted from GTPU extension header to the SDAP header, flow ID, because you need to recognize the flow, or vice versa. It is getting shifted from SDAP to GTPU header, GTPU extension header. This is present in both uplink and downlink directions. But your RQI related information is applicable only in downlink. So only network can send you enabling RQI, reflective quality of service, to be enabled in uplink. So it is kind of network is commanding you by sending downlink information to enable uplink quality of service on this particular QoS flow. Same uplink quality of service you need to enable, whatever that is applicable in downlink. But that is network sending, that is why it is present only in downlink. That is not present in uplink. Uplink, the first 2 bits, only 1 bit is being used, device E, which tells data or control. This is reserved bit, which is useless. Device E, when it is set to 1, it contains QFI. Next 6 bits contain the QFI value, which can be a value ranging from 0 to 63. Here also 0 to 63. 64 QFIs can be there. Quality of service flow identities. And then followed by data. But when the device bit is set to 0, it represents SDAP control. I have told you, every layer can send control information. We have control mechanism in PDCP level. We have control mechanism now at SDAP. We have control seen in RLC, standing status reports. So every protocol layer, protocol to protocol related control information can be exchanged. Now, what is this control PDU when the device is set to 0, reserved anyway is ignorable? You are sending the QFI with the device is set to 0. For example, QFI can be 5. What is the meaning of QFI sending 5? That is representing end marker. End marker means, hey, on this QoS flow number 5, I'm now stopping sending the data. This is the last one I'm sending. So end marker means you are kind of reporting in uplink direction, only this is possible. Mobile is reporting to Gnode that, hey, on this particular quality of service flow, from now onwards, I'm stopping sending the traffic. Why I'm stopping? My reasons are there. I have my reason for it. But I'm indicating you that I'm stopping the traffic on this quality of service flow. from now onwards. So it is kind of getting inactive. When it will happen, we'll study it in the next slides, next set of slides. We'll study that. But no header, no SDAP header with header. Downlink header is different, uplink headers are different. Only in uplink we have control. That's why we have device applicable only in uplink, not there in downlink. Downlink, only 2 bits represent related to reflective quality of service indications. One to apply the reflective quality of service, other one is to report NAS about it. QFI. But in uplink, we have D by C QFI, reserved with the reserved bits, the middle ones ignored. If you send D by C set to 1 and send the QFI, it is containing the data, belongs to higher layer, your IP packet. But when it is set to 0 and QFI, then higher layer data won't be there. Mithilesh, I did not dismiss you. Sometimes when it is linked to wrong audio, it will get dismissed like that. Okay, don't worry about it. Anyway, you rejoined, so you can continue. So your machine somehow connected to wrong audio. Okay, Mithilesh. Okay, let's continue. Now, when does mobile send this end marker in uplink? So, what are the different rules related to this SDAP? Who configures it, and etc. The points related to it. When RRC configures the uplink quality of service flow to DRB mapping rule for a QoS flow, what does the SDAP entity shall do? So RRC told the SDAP that so-and-so quality of service flow should be sent on so-and-so DRB. Then what is the job that SDAP must perform? So these are the rules and regulations related to it. If the SDAP entity is already established earlier itself, and also there is a default DRB configured already on which you are sending the traffic so far, because till now your quality of service flow is not required to be sent on any particular DRB. You are sending it on the default DRB so far. So in already SDAP entity is there, default DRB is there. In this case, because RRC told the SDAP that you have to start using the new DRB for sending this uplink quality of service flow, immediately SDAP construct a end marker for this particular quality of service flow ID and send it on the default DRB. Because so far you have used the default DRB for sending the traffic for this particular quality of service flow. But the moment RRC told you that, don't use the default DRB for sending it, I'm configuring a special DRB for achieving good quality of service. From now onwards, you use the special DRB. The moment RRC told this to the SDAP immediately generates end marker and send that end marker PDU on the default DRB, explaining that, hey, my quality of service flow ID is 5. Till now, I have sent the quality of service flow ID 5 related data on the default DRB, but from now onwards, I am stopping it. I am going to send it on the special QoS flow, special DRB that is getting created for me just now, specially. On that, I am going to send this data from now on. That is what is going to be indicated. So you make such kind of an end marker PDU and you send it to the PDCP protocol, the lower layers. Lower layers will dispatch that to the other side. Other side SDAP gets this, understands that, Okay, from now onwards, this bugger is stopping sending the traffic on default DRB for this particular QoS flow. It is going to send on the special DRB that is just now enabled. So I have to look for the data belongs to this QoS flow on this new DRB that is configured. So the receiving SDAP will understand the situation, what's going on. Now, suddenly if the QoS flow to DRB mapping rule is different, changed, it is not getting freshly configured, new DRB is not getting freshly configured, but if it is getting changed, even when it is getting changed, similar kind of a job will be done. You prepare a end marker and you send it on the quality of service flow that you are on the DRB that you are earlier using, whichever DRB that you are using earlier. For example, you are using one quality of service, suddenly you change the quality of service. So network decided to create a new DRB for you. You have to shift your quality of service flow to the new DRB. So whenever you are doing that, you have to indicate that you are going to stop sending the traffic on the old DRB by sending this end marker PDU. Please remember, this end marker, we are studying it, the SDAP end marker. We have GTPU end marker, which is different, the SDAP end marker, which is different. SDAP end marker is to tell that on the DRB, we stop sending the traffic belongs to this QoS flow. So now you have to apply the new rules, new mapping rule by stopping the old mapping rule. First, you prepare a end marker and send it on the old DRB that is mapped to your QoS flow. After sending it, you will kind of start using the new mapping. The QoS flow would be sent on new DRB, whatever that is configured. But if network tells you to one mapping rule is discarded, releases, you discard them. You simply throw that rules and you discontinue that operation. This is when a new DRB is created by the RRC for your QoS flow, or your existing DRB has been modified to a new DRB. In those cases, how exactly SDAP have to behave? It will have to send the end marker on either on the default DRB or already whatever the DRB that you are using, and you have to shift it to the new DRB. Map the QoS traffic, QoS flow traffic to the new DRB that is created for your purpose. Okay. What are the SDAP rules in case of reflective mapping? Reflective mapping means traffic is arriving in the downlink direction. You have received the SDAP data in downlink. We are talking about RDA and RQI. RDA is set to 1, RQI is set to 1. We are talking about that situation. So you receive the downlink SDAP with RDA set to 1. Then what you are supposed to do? You process the QFI field and identify which QoS flow for which we are receiving the downlink traffic. For that QoS flow, if you are not sending any, if there is a default bearer is already configured for it earlier, if you are not sending any uplink traffic on any special DRB, but you are sending it on the default DRB, immediately you prepare a end marker and send that end marker on the default DRB. You tell that because the reflective quality of service is configured, from now onwards, I'm going to send this quality of service flow on this same DRB that I'm using right now. I'm not going to send it on the default DRB. So far, I have sent it on the default DRB. Default DRB's quality of service is different. The downlink DRB's quality of service is different. You have two DRBs. One is default, one is downlink one. So for downlink, you are using a special DRB. Uplink data you are sending on default DRB. But the moment you got this reflective quality of service indication, immediately SDAP understands that for sending the uplink traffic belongs to this application or the quality of service flow, I have to stop using the default DRB. I have to stop using the same DRB right now, whatever on which I have received this command, on which I have received this RDA bit set to 1. So, but before that, I have to indicate this to the GNodeB about it. So you prepare a end marker control PDU, send it on the default DRB, explains to the GNodeB's SDAP that, hey, I have applied the uplink reflective quality of service for this guy. From now onwards, all the uplink traffic I would be sending on the same DRB. Now this DRB will have both uplink mechanism as well as downlink. Earlier, it might have been using only downlink. Now it will have the uplink also implemented. Same data rate need to be present on the uplink. Of course, corresponding radio bearer configuration would be done by the GNodeB before it is ordered to the mobile to implement this mechanism. At MAC level, at RLC level, at PDCP level, the corresponding changes would be done. Okay. But for that reflective thing, if you are using a separate DRB other than the default one, you are using some other DRB. Now on the DRB, you send the end marker. And then you continue with the new DRB, whatever that, the same DRB that you use for sending uplink also. That means earlier, to receive the downlink traffic, you are using one DRB. To send uplink traffic, you are using one DRB. Why? Downlink data rate is different. Downlink quality of service is different. Uplink quality of service is different. But the moment you get RQA indication, you have to use the same DRB, same data rate. The downlink data rate is same, uplink data rate is same. You are going to use a single DRB for it. So you send a end marker on the previously being used DRB. You report the end marker and you start using the new quality of service flow. If this is the case. So ultimately, which DRB you have to use for which quality of service flow can be identified by SDAP in two different mechanisms. One, RRC configuration. RRC tells you like which QoS flow need to be mapped onto which DRB. Second, the RDA and RQA bits. RDA bit is set to 1, then you have to use the same DRB that you are receiving the downlink traffic on, which on the same thing you have to send even your uplink traffic. If you are using any default DRB or any other DRB earlier, you have to stop using them and send the end markers on them, and you have to start using the same DRB that you have received this RDA request on. So two different ways SDAP can get indication on which DRBs to use your uplink traffic, either from the RRC configuration or from the RDA. In case of reflective quality of service implementation, but this is applicable only for uplink. Now DRB release, again, when RRC indicates you to release the DRB, you release the DRB and whatever the QoS flows that are linked to the DRB, all of them will be dropped. They are all released. All those QoS flows will be released. Because if DRB is dead, if DRB is carrying 3 QoS flows, now these 3 QoS flows cannot travel now on the DRB anymore. So you have to remove those QoS flows also that are associated with this DRB. RQA handling, for every downlink SDAP PDU, if RQA is set to 1, you have to go and speak to the NAS layer about it. Inform the NAS layer that RQA is set for this particular QFI. Reflective quality of service is enabled. You kind of needed to report it to NAS whenever it is set to 1. What NAS does with it, that's a different story. But you SDAP need to report it to NAS. So the ultimate summary of this is when your IP flows arrive, by using the IP packet header information like IP addresses, port numbers, etc., you will recognize which traffic should be sent on which QoS flow. Put that QoS flow information in the GTPU header with the help of PDU session user plane protocol and send it on N3 tunnel to GNodeB. GNodeB extracts that QFI IDs and shift them onto SDAP, where it is sending that information on the DRB. But on which DRB you have to send it will be dependent on the already pre-configuration that is either done by RRC or on the basis of any other details like reflective quality of service mechanisms. But in case of downlink, it is done by RRC. So you identify that corresponding data radio bearer and dispatch that traffic by including the QFI ID. So you are getting the QFI ID from the N3 tunnel, the GTPU, you are shifting it to SDAP. SDAP packs that and send it to the mobile. So mobile receives for which QFI it has received the traffic. If it is asked to reflect the same thing in uplink, it can do that also. So we have completed this mapping mechanism of how this QoS flows to these SDF rules, to QoS flows to tunnels to data radio bearers, and which protocol layer will do what role. So how this filtering works out, we have completely studied that. How the IP flows will arrive, they will be converted into QoS flows. How the QoS flows are mapped onto DRBs, data radio bearers. On the receiving side, how from the DRBs, how you will be able to extract the QoS flows, identify if the data belongs to which QoS flow with the help of SDAP header, and then dispatch them to the higher layers. IP flows would be sent to the higher layer. At each node, how the job is done, we have studied that. Now there is one last part pending, which we'll cover today only. Just hold on. I'll open that. Okay. I hope you remember this, the one that we have introduced yesterday. What is part of a radio bearer? Radio bearer is a process that is containing the PDCP and RLCs doing corresponding process. They're doing their duties, sending the data to MAC layer on the basis of MAC requests. But we learned that MAC need to do some kind of a prioritization, logical channel prioritization. Based on the resources it has acquired, MAC layer will do the prioritization on the basis of the priority values. What is the priority values? We have learned that priority values today. For every 5QI, so whenever a radio bearer is getting created, it is, or anytime any QoS flow is getting created, that QoS flow is associated with 5QI. There are different 5QI values. For each one, we have a different priority. We have learned that part already. We have seen these tables, like for which 5QI, what is the priority level? For conversational voice data, priority level value is 20. For video calls, the priority value is 40. For real-time gaming, the priority value is 30, etc. If these three guys fight for the same resource, if enough resources are not there, who will win in that is definitely voice traffic will win. So logical channel prioritization will work on the basis of these priority levels that are associated with each QoS flow. Each QoS flow is typically would be put onto radio bearers, or nothing but one logical channel. What is the QoS default priority value that is applicable? Okay, but that is after allocating the resources. This fight will take place after resources are allocated, and that too if all of them are present at the same time. This fight will happen. Who have to get the resources? For example, all these three things are there. You got very less resources allocated by MAC after scheduling. Now you have to decide whose data you have to send. Obviously, priority will come into the play. Higher prioritized guy will be getting the advantage. That guy's data would be sent first. If any space left out, then the next priority guy, then the next priority guy. It is like that. Okay. First of all, how the resources will be allocated. So we have to understand how the resource allocation will take place, how the scheduling works out at the MAC level. So let me summarize. So far we have learned about if the quality of service flows are existing, somehow MAC will do the prioritization because there is a priority value associated with each quality of service flow. MAC can do that job, but MAC does that job only after allocating the resources. G-node-based MAC layer need to allocate the resources for many subscribers. After individual subscribers got the resources, that subscriber may have a lot of radio bearers. Then by doing the logical channel prioritization, you decide to which logical channel we have to allocate the data. You kind of can sub-segregate it. But first of all, when a lot of subscribers are fighting for the resources, how the G-node-based MAC layer allocate the resources to the subscribers. So that is the meaning of scheduling mechanism that we have to study. Be patient with this, guys. We are going to take 1 hour more because we are lagging in subject. I want to desperately complete this. Okay. First, to do the resource scheduling for the subscriber, the G-node B, not E-node B, G-node B, G-node B will have all these details available at G-node B's MAC layer before performing the downlink scheduling. What is it? What are the total number of resources that are available? Like the total number of resource blocks. Maybe if you are operating on very high, huge bandwidth like 100 megahertz, you will have more resource blocks. If you are operating on 5 megahertz, 10 megahertz operating band, then you will have less resource blocks. But ultimately, G-node-B's MAC layer know for downlink operation how many resources are there. Of course, same thing in uplink also. For uplink scheduling also, how many resource blocks are available? That is known. Now, G-node-based MAC also know what are the UE's capabilities, what and all things UE can do, what is the memory capacity of the UE, how much time mobile can, how much data mobile can process at a time. When you are packaging huge data and sending it to mobile, can mobile deal with that or not? So that those are called as capabilities, downlink capabilities. In downlink, mobile should be ready to receive even huge amount of data when it is scheduled from G-node-B. In uplink, mobile must be able to host huge amount of data in its buffer if you have to keep it pending, for example, without allocating the resources. So how much more data the UE can keep it in the buffer? How much buffer is available? Or even in uplink, how much amount of data mobile can process and send at a time, at one time, if you are allocating huge amount of resources. So you kind of need to know the UE's capabilities that will play a very important role in the scheduling algorithms. Each UE will have a buffer, the amount of data that is present in the logical channels. And for each logical channel, there is a priority, there is quality of service properties, and what is the delay, data delay, already how much time the data is delayed, waiting in the buffer. So all this information you know before you are scheduling. And for each UE, uh, GNODB also knows the reported CQI values and rank indicator values, channel quality information and rank information for MIMO operations. Whether mobile is reporting good channel quality or bad channel quality conditions. What is it? So all these details, so everything will go into scheduling algorithm as input. So scheduling algorithm will have to consider everything and then we'll have to come out with a decision like which users are scheduled out of the fightings, many subscribers that are present. How many resource blocks are getting allocated to each subscriber in time domain and frequency domain, and what is the MCS value, modulation and coding scheme number, MCS number kind of determine what is your transport block size. So you'll have to come up with these details after scheduling is applied, scheduling algorithm is applied. Uplink also similar details. You will get to know the buffer status from the mobile in the form of buffer status reports, group wise. Individually, logical channel wise, you don't have. For a downlink, you will have individual logical channel wise. Because in downlink, GNODB knows how much data is waiting for the mobile for each logical channel. But for uplink, mobile need to report it to GNODB. Mobile would be reporting it group wise in uplink. But who does the resource allocation is GNODB, even though mobile is reporting it. Channel quality estimations on the SRS, sounding reference signal. Uplink sounding reference signal, mobile is transmitting, from that GNODB is estimating the channel conditions. We studied this SRS part. Power headroom. Mobile require how much power to transmit the uplink signal versus how much it is right now you're using. So that ratio is what we call as power headroom report. I told you this earlier. So even if mobile reported that it has got good headroom, that means mobile has got good power, but it is using only less power to transmit the signal. That means mobile is in good conditions. So you can configure more resources for uplink for the mobile. So this power headroom report will be kind of considered in scheduling algorithms as a one factor. The mobiles with higher power headroom will be preferred because they are in better conditions when compared with the users who are with reporting very less power headroom value or negative power headroom value. So again, everything will be considered and put into scheduling algorithm that will come out with a result explaining how many users are getting scheduled, and for them what resource blocks are getting scheduled, and what is their MCS size, modulation and coding scheme. So these details would be packed in the form of DCI, downlink control information, either DCI 10 or 00, depending on uplink or downlink, and it would be dispatched to the mobile on PDCCA channel after allocating the resources. But to allocate the resources to different subscribers, what are the different techniques that are available? So I was asked to introduce those different designs, different models, different scheduling mechanisms. One by one, we'll see. A very, very interesting topic. So the first mechanism is called as round robin scheduler. Very, very easy way to implement the scheduling algorithm. The algorithm starts, it schedules the first user, whoever comes first. And after that is completed, first user is completed, it will go to the next user. Like that, this operation will keep continue till you check a condition. Have all the users have been scheduled or not? If not all the users are scheduled, you go to the next user. So you first schedule one user, next user, you check this condition. If all the users are scheduled, yes, you will go back to the first user. If not, you schedule the next guy. Let us assume there are 6 guys. First you scheduled one user. Then you move to the next guy. Scheduled him with some resource. Everybody will get equal resources in round robin. After that, you check other users are there or not. All the users are scheduled or not scheduled? Not scheduled. 4 more guys are still there. So answer is a no. When it is a no, you schedule the next guy. Again check. All the users are scheduled? No. Still 3 more guys are there. Next guy. Next guy. Next guy. Once all the users are scheduled at least once, have all the users been scheduled? Answer is yes. One time happened. Now you are going back to the first guy. You start with the first user once again. So repetition. So that is what is round robin. In a circular way, you will allocate the resources to the subscribers. Now in this, you never care about these subscriber related channel conditions. Ignoring those channel conditions, we would be allocating the resources sequentially one after the other and equal number of resources. So this algorithm, this scheduling algorithm is called as channel independent scheduling algorithm. Because we are not caring about channel conditions, some users will get low throughput, some users will get high throughput. For some users, there will be a lot of bit errors. Because everybody is getting equal resources without worrying about, without caring about their radio conditions. Their CQ values are kind of ignored in this scheduler. We won't use this scheduler. I'm just introducing different schedulers. So resources are allocated to the UE sequentially. It is considered as a high fairness algorithm. What is the meaning of high fairness? While allocating the resources, you are following fair rules. That means everybody is getting equal opportunity. All the mobiles are getting equal opportunity. In terms of radio resources, their radio resources are equal doesn't mean that their throughput would be equal. It may not be, because some users may face radio problems, radio errors, because their quality is bad, channel conditions are bad. Other users might not. So their throughput may not be the same, or the service quality may not be the same, but their allocated resources are the same. As we are finding some kind of a round robin fashion. It is a easy to implement algorithm, but system performance is very bad. Overall system performance is very, very low, because without worrying about radio conditions, we are allocating resources. So that is not a good idea for achieving good system level mechanism, system level quality. So it would be done first come, first enter the scheduling queue basis. Resources would be allocated. And you don't consider the quality of service requirements of each subscriber. If one guy requires some particular quality of service, we don't care, because it's equal resource allocation technique, where everybody would be getting the same resource, same amount of resources. Very, very fundamental algorithm, guys. It is not used in modern systems, but simply introducing different possible algorithms. Of course, it is used indirectly, not directly it is used, but indirectly it is used in our advanced systems, for sure. How? I'll pinpoint that later. Second scheduling algorithm, while allocating the resources to subscribers, called as MAX-CA in shortcut, maximum carrier to interference scheduler. That means it will care about channel quality conditions. You see 3 lines here which represents the CQA values. Yellow color is the CQA value of the first user. Gold color is the CQA value of the second user. Green color is the CQA value of the third user. Their CQAs are changing because they are moving in the network from place to place. Their channel quality conditions are changing. But now the white color line represents the resources are getting allocated to which subscribers. If you observe, Whichever user CQI is better at that time, that guy will get the resources. So if you take a look at till this particular time, in this particular position, definitely user 3 will get the resources because user 3 CQI is highest. You see there. The green color one is on the top. That represents that the green color guy's CQI is the better compared to the gold color or yellow color. But after some time, gold color CQI increased more than the green color one. Green color CQI dropped. Yellow color is continuing on the same lines. So now what happens? The resource allocation kind of from year to till this particular step, till this point, the resources would be allocated to the gold color guy, that is second user, because second user's CQI is the highest in the duration. So simple algorithm, whichever user CQI is better, that guy will get the resources continuously as long as that guy's CQI is better than the other guys. So you keep comparing the CQI values of several subscribers. Whichever user's CQI is better, that guy will get the resources. Simple point. Now, this is called a channel dependent scheduling algorithm. Users are scheduled based on their maximum carrier to interference value, nothing but CQI value. It optimizes the system capacity because you are always sending the signal in good conditions. So you are allowed to use higher modulation technique. Your total overall system capacity will be very high. It will be really, really good. Because you are always sending good channel, good signal to subscribers. There is no possibility for any errors. And you are allowed to use higher modulation. Because you are always scheduling the data to the subscribers at their higher CQI values. We already learned in the previous classes that when you are having higher CQI value, you are allowed to use higher modulation. We learned that as adaptive modulation and coding, if you remember. But this is bad for some users. For example, if some users are experiencing bad channel conditions, if their CQI is not improving, they will never get the resources. So it is called as a low fairness algorithm. It is low fairness because it's not fair to some subscribers, for some users. As it is showing the partiality to the subscribers who are having higher CQI value. But for implementing this algorithm, channel quality feedback is important for implementing this algorithm. On the basis of channel quality only, you would be able to do the scheduling. But it won't consider the quality of service requirements of each subscriber because the resource allocation is purely taking place on the basis of your CQI values. Whichever whose CQI value is higher, that guy will get the resource. Not on the basis of which guy requires which quality of service, what data rate is needed. Is not on the basis of that. So to improve the overall system capacity, this is a good algorithm. But it won't be serving individual needs of the subscribers or individual quality of service of the subscribers. And it won't be good for some subscribers who are having lesser CQI values, who are experiencing bad channel conditions. Okay. Again, is this the algorithm that we use? No. These are all fundamental algorithms. We use much complex algorithms, which I am going to introduce. Next algorithm is proportional fair. A user K would be chosen on the basis of what data rate can be achieved for that user at this particular time by using its channel conditions, reported CQI values, what data rate you can achieve, How can you decide one user's data rate is based on its CQI, what modulation you can use, how many resource blocks you can allocate to that guy. Based on that, you can identify this, what is the achievable data rate for that particular subscriber based on its present channel conditions. What data rate you can achieve versus Ri of t, which represents already what is the average data rate that is provided to that user over a time window in the past values. This is what in the past, what data rate you have provided to this guy, what you can achieve for this guy at this particular point in time versus what is already provided to the subscriber. So you kind of take the ratio of the two values for every subscriber, and whichever subscriber's value is the maximum value, for that guy you will allocate the resources first. We'll kind of dig deep into it to find out the more details there. Can anybody tell me what is the logic behind this? Just try to participate. See this here. This is the data rate that you can get in the present situation. This is the data rate that you already got earlier on the channel. Why are we doing a ratio, and why are we finding out the K value on the basis? So you will find out K1 for subscriber 1, K2 for subscriber 2, K3 for subscriber 3, K4 for subscriber 4, K5 for subscriber 5. Whichever K value is the highest, that guy will get first preference. That guy will get the resources first. So now tell me, what is the logic behind it here? Anyone can tell me what is the logic that is lying inside that formula? Try to participate, guys. Okay. Simple idea here. If you already got huge amount of data rate earlier in the previous time units, this value will be high. If the denominator is high, automatically the value will become low. If you understand the numerator and denominator, if numerator is high, the output will be high. If numerator is high, if the denominator is high, the output will be low. That's common mathematical thing. For example, if you take 5 by 15 by 3, you take value is 5. In this case, numerator is high, denominator is low. But if you take 3 by 15, it would be completely different. The value would not be 5. It would be in decimals, whatever you get. It's very low value because denominator is high. So anytime denominator is high, the K value will be reduced. K is the comparison factor here among multiple subscribers. That means if you are already got huge amount of data in the earlier situations, you will be given less preference. That is the proportional fair means. That means it is fair to everybody. It is fair to everybody in a sense where everybody is given some amount of preference, some amount of fairness. Everybody is being considered. Now, in the previous time, some X amount of time unit, the average data that you have received is kind of reduced because you got resources long back. For quite a while you did not receive the resources. So your previous resources you have received is low. So previous received data rate is very low. When your previous received data rate is low, what you can achieve right now is high, or which is considered as Ri of t, definitely the K value will be higher. So for the subscribers who are not getting the resources continuously, their K value will be incrementing. For the subscribers who are getting the resources continuously, their K value will be decrementing. So you will be balancing this K value among multiple subscribers. when they are continuously getting data scheduled, their K value would be decremented. When they are not getting scheduled for some time, their K value will be incremented. So on the basis of it, you will be balancing it out. But here, the data rate will be dependent on how much data can multiple users have the same K value. It is very highly unlikely. If multiple guys have the same K value, you will compare who entered first into the scheduling algorithm. Maybe we can allocate the resource to that guy first. Because you won't allocate all the resources to a single guy anyway. You can allocate the resources for both the guys, even if multiple guys have the same K value also. Now, the resources are allocated on the basis of your previously achieved data rates without worrying about your quality of service that you require. Any time that you are not caring about quality of service, definitely not good for real-time services. It is only good for NRT services, non-real-time services, or non-guaranteed bitrate services. For guaranteed bitrate services, this is not good. Because you are not considering the promised data rate. You are only considering what is the data rate that is achieved in your system for you earlier versus what you can achieve now based on the present channel conditions. So definitely this is taking channel conditions into the consideration. But the thing it is not taking into consideration is required quality of service. It is not worried about QoS. Okay, next algorithm. This is proportional fair. Okay, next. Before introducing the next algorithm, I'm going to introduce one particular parameter in 5GNR. We already know guaranteed bitrate, GMBR, or GFBR, guaranteed flow bitrate, are simply called as guaranteed bitrate. Guaranteed bitrate kind of divided into PBR and BSD. Whenever there is a guaranteed bitrate service that is applicable, the relationship among them is the formula that is appearing here. GBR is equal to PBR into 1000 by BSD. It should satisfy this. I will show some examples so that you will get the idea behind it in a table. Let us suppose that your guaranteed bitrate is 1 Mbps. But bucket size duration is decided to be 1000 milliseconds, which is equal to 1 second. Your data rate is 1 Mbps, which is meaning is you have to send 1 MB of data per second. So your prioritized bitrate is 1 MB itself. In order to dispatch 1 MB, you have, for example, 2000 TTIs available. Every slot we can transmit the resources. We can allocate the resources. Slot size is 0.5 milliseconds if you take 30 kilohertz ACS, your RIL case. So you have 2000 slots in 1 second duration. Because slot size is 0.5 milliseconds, 1 second is equal to 1000 milliseconds. You have 2000 slots. So there are 2000 transmission opportunities to dispatch 1 MB of traffic. But what is the meaning of bucket size duration? To dispatch this bucket of size 1 MB, how much time you have? 1000 milliseconds you have. But when to schedule it? You can wait for 999 milliseconds without allocating any resource. In the last 1 millisecond, you can dispatch the entire 1 MB. Still, it will be considered as 1 Mbps data rate. Still, it will be considered as achieving the GBR, guaranteed bitrate. But when the bucket size duration is going down, the approach changes. You have GBR 1 Mbps. BSD is only 500 milliseconds. That means half a second. Every half a second, you have to dispatch 0.5 MB. That means in the first half of the second, you have to dispatch 0.5 MB. In the second half of the second, you have to dispatch another 0.5 MB. You cannot wait for 999 milliseconds and the last 1 millisecond you cannot dispatch entire 1 MB. You are not allowed to do that this time. Because your bucket size duration is halved, only 500. So every 500 milliseconds, you need to dispatch 0.5 MB. By doing so, you are achieving 1 Mbps data rate, 1 MB per second. So applications will determine what is their BSD value. 100 milliseconds, 0.1 MB. 50 milliseconds, 0.05 MB. 20 milliseconds, 0.02 MB. 10 milliseconds, 0.01 MB. The meaning here is, last one I will tell you, every 10 milliseconds once you need to dispatch 0.01 MB traffic. So you cannot wait for 999 seconds and then milliseconds and then you can configure the resources. No. Every 10 milliseconds once, duly you have to dispatch 0.01 MB of traffic. So you have to send regular intervals. Every 10 milliseconds, a piece of it you have to send. By doing so, you have to achieve 1 Mbps traffic. You cannot say, hey, I will send all of it at once by making it wait. Now we will try to figure out the advantages and disadvantages of these approaches. In this approach, what is the advantage, disadvantage? Advantage, you can perfectly do dynamic scheduling. For example, if any particular subscriber's radio conditions are not good, you can make that guy's data wait. At least for 1000 milliseconds, you can wait for 1 second. At least till you can wait to see if that guy's channel conditions become better. As you have enough time to wait, enough time available to wait. As the BSD is long, bucket size duration is long. But in this scenario, even if the channel conditions are bad for a subscriber, as you have a duly bound duty to send 0.01 MB of data every 10 milliseconds, even the channel conditions are bad, you have to schedule the resources for this guy. You can't make it, kind of keep it on the buffer for too long. As the BSD size is very small, application demanding that the data need to be dispatched in regular intervals. So different applications generating different types of traffic will have different BSD values applied. And your scheduling have to adjust to that BSD and achieve the guaranteed bitrate by sending the corresponding amount of data within that BSD time. Is this clear? Everybody got this? Any questions here? Because you have to understand this. Without understanding it, you won't understand any of the next things I'm going to introduce. Any questions? Anyone in this slide? Ask me now. So whenever network is configuring a guaranteed bitrate for the subscriber, it will not ask the entire data to be sent in one shot, but instead, network will ask that it must be implemented in a small durations called as bucket size durations. Every bucket size duration, you will have to clear PBR data, prioritized bitrate data, you have to dispatch. So if every 500 milliseconds you dispatch 0.5 MB, in 500 milliseconds you send 1 MB. Every 100 milliseconds you send 0.1 MB. You have 10 such opportunities. You will dispatch 1 Mbps traffic totally, 0.1 in every 100 milliseconds. Next 100 milliseconds, 0.1. Next 100 milliseconds, 0.1. Like that, you have 10 opportunities for 10 into 100 milliseconds is equal to 1000 milliseconds. But every 100 milliseconds, you are dispatching 0.1 MB. Your effective rate is 1 MB. So whenever guaranteed bitrate services are working, they'll always be associated with this BSD and PBR configured, either for downlink or uplink. Downlink, it would be done internally inside the Gnode B. Uplink, it is configured on the mobile side. What is the BSD value and what is the corresponding PBR value applicable for the GBR? and you have to follow those rules strictly and send that much amount of data applicable for that particular BSD. You must clear this PBR every BSD. It's mandatory to achieve this GBR. Here, GBR is none of them are fixed. You can reconfigure the radio bearer that is already configured. But if application is kind of generating the fixed amount of data, all of them are fixed. Application knows how frequently it is generating the data or how frequently it would like to receive the data. On the basis of it, application sets this BSD and PBR by setting the GBR. We cannot kind of say that which one is fixed. But I can tell you this way. First, GBR will be decided. Then on the basis of the application property or how frequently it wants the data, on the basis of that, BSD and PBR will be decided. But first, GBR will be decided to make you that point clear. Understood? Okay. Now remember, for example, we are under this BSD 20 milliseconds approach. Every 20 milliseconds, you have to kind of schedule the resources to dispatch 0.02 MB of data. Every 20 milliseconds once. In the first 18 milliseconds, we have not scheduled the resources for this guy. Now you have only next to 2 milliseconds or 4 slots available to schedule the resources. Only 4 slots are available to dispatch 0.02 MB of data. If those 4 opportunities are also finished, then you are basically violating this PBR and BSD rule. That means you are violating GBR rule. That is kind of considered as a violation. If the data is not scheduled within that BSD expiry time by achieving that PBR within that BSD. Now, this BSD kind of a ticking bomb in terms of scheduling. For whichever subscribers BSD is approaching, we have to give them higher priority. Their BSD timer is about to expire. There are no more scheduling opportunities. So this kind of need to be considered in the scheduling algorithms. Earliest deadline first. Algorithm name is EDF. Here the criteria K value would be chosen maximum value of 1 by Ti minus DHOLI. Ti is what is the maximum packet threshold that is applicable for a data which is typically your packet delay budget minus already how much time it is already it is waiting in the buffer. Head of line delay happened already. That means it is waiting in the buffer. How much time it has already waited in the buffer. The value becoming lesser, this minus this is becoming lesser. For example, I will put some numbers to it. Packet delay budget is 100 milliseconds. Already it is waited in the buffer for 85 milliseconds. The value will become 15. It is becoming 1 by 15. Now, packet delay budget is 100 milliseconds. Already it crossed 90 milliseconds. Now it becomes 1 by 10. Now if you take a look at 1 by 15, 1 by 10, which one is bigger? Definitely, which one is bigger, guys? 1 by 15 value is bigger or 1 by 10 value is bigger? Tell me before I write the next one. For example, already 95 milliseconds crossed. So it becomes 1 minus maximum is 100 minus 95, 5. So tell me, 1 by 5 is bigger or 1 by 10 is bigger or 1 by 15 is bigger? Simple mathematical thing. Definitely 1 by 5 is bigger. So that means The user which is having the bigger value will be configured first. The meaning is whichever user is um, getting configured first, that guy is definitely is the ticking bomb is nearby. So when the value is smaller, DHOL value is smaller, the denominator part will become smaller. When the denominator is small, this argument value will be big. Because when you divide anything with one, when you divide it with bigger values, the small value output will be small. When you divide it with small value, the output will be high. Output will be big. You have to take the bigger value here because this is argument max. Whichever user's maximum value is having, that guy's data will be scheduled first. So this algorithm, earliest deadline first algorithm, is not considering the channel conditions. It is simply on the basis of users' quality of service implementation, only taking care of QoS. Because QoS only will derive these deadlines. When it is going to expire, when the timer is going ticking, the more closer you go by to the timer expiry, the higher priority that it will get. But so far, all the algorithms we have seen are kind of either channel conditions or quality of service, but not both. Earlier ones we have seen are only taking care of just channel conditions or just resource distribution. This one is taking care of quality of service implementation. Whichever user guys data is approaching deadline first, that guy's data we are scheduling first. But later what they decided to do, mix them up, mix these algorithms up to achieve both. So one such algorithm is called as modified earliest deadline first proportional fair. So this is kind of mixing earliest deadline first, the previous one we have studied, which works on the timer ticking, proportional fair, which is working on the previously allocated resources plus what you can achieve now. So it is kind of combining both. So it is taking the ticking value, the deadline value, plus what is already allocated to the subscriber. If already a large amount of data is allocated, that guy's ratio will go down. If the time is ticking, this guy's data will go up. Both are actually conflicting each other. But whichever is giving you higher value, that will define your higher K value. That will make higher K value here in the argument max. Now, this GFT is kind of increasing concave value. Concave function means ever increasing value is called as concave function. So if the time is ticking, if the more and more delay is occurring, on the basis of it, you take a concave value. So that value will also incrementally increase. This is the maximum argument. So if the delay is increasing, your argument value would be increasing further for the subscribers. So you are not only taking comparison of all the subscribers, but individually each subscriber's delay in the exponential value in the form of a concave curve, the slope value that can be tuned. You can decide what is this GA concave size or how rapid it will increase on with the basis of the amount of delay occurring. But ultimately, if you consider the algorithm, delay is playing role, and what are the previous resources allocated, what you can achieve now. This array of T is telling you what you can achieve now. All of them will be considered. So we are considering channel conditions because you know what you can achieve now, what you achieved earlier, what you require now to complete your time ticking. Everything we are considering, and whichever subscriber is getting bigger argument output, that guy's data would be chosen first. That user will be selected first into your scheduling. Next, one more algorithm. Modified largest weighted delay first. It's called as the largest weighted delay. It is not delay, it is weighted delay. What is the difference between delay and weighted delay? This WI of T will be considered as delay, your head of line packet delay in one teeth TTI. This U of I is the achievable data rate for your channel conditions. U bar of I is the previously achieved data rate. So this kind of considering the channel conditions. What can be achieved now? What is already allocated to you? And this is the head of line delay that is occurring for your packet. Plus, there is this AI. This AI is applicable for weighted delay. This AI is kind of considering what is the largest probability for the delay requirement can be violated. I already told you. If you are violating the BSD, bucket size duration, that will be considered as violation. If the probability of the violation is increasing, AI value will increment. If the AI value will increment, that will increment the K value. That means when the tick is coming nearby, when the number of scheduling opportunities are reducing, the probability value will be increasing. Probability will be based on how many more opportunities you have for your transmission scheduling. If the number of transmission schedulings are reducing, the probability will increase, the AI value will increase. That will determine the K value to be rapidly increasing based on this probability drop. So that kind of goes in here. So you're kind of considering the delay, but weighted delay. That means you are not only considering how much time it has waited so far, but you are also considering when it is going to expire, what is the probability for expiring. That also you are considering into your algorithm. And then on the basis of it, you are selecting whichever subscriber's K value is higher, whose time is ticking nearby, whose probability, whose time ticking is going to be violated, that guy will get more priority in this. Another algorithm. Okay. One more. Exponential proportional fairness. Another algorithm. What is this? This is kind of proposes an exponential method, exponential way of increasing the maximum value for RT services, but using normal mechanism for NRT services, like what is achievable, what is achieved. That is applicable for NRT services. Because NRT services can wait, no problem. There is no time ticking for them, non-real-time services. But for real-time services, time ticking. Your waiting time matters, already waited time. Your probability matters, AI. What is the probability for the violation, time violation? That matters. Plus, already AW bar is what happened in the previous timers. What was the violations earlier? So the average of it, you will take the previous averages. You take those previous probability averages. You take that value also into consideration, and you apply an exponent to that. Anything to the power of E, for example, if it is E to the power of 5, E is kind of, we have a value 2 point something, E value. To the power of 5, you get 32. That will exponentially will increase K. If the value is increasing to 6, for example, it is E to the power of 6. So K value will be even more. So when the delay is increasing, when the probability of failure is increasing, when previous probabilities are suggesting you that there is previously there are violations occurred, everything will pinpoint to a bigger value. So when the value is becoming bigger, then you will be sending, you will be giving priority to that subscriber even higher. Exponentially, you give priority to that subscribers. So this is what you can achieve now versus what is already achieved. So this is considering the channel conditions. This is what you can achieve now, what is already achieved, what is provided to you. So you are proportionally allocating the resources to this guy, but also considering that guy's packet waiting time in the buffer and what is the probability for its failure in terms of violation. Plus, what is the average failure happened earlier? What are the violations happened earlier? Based on it, you are finding exponential part. And you're multiplying that to the proportional fair already. So obviously the value will be bigger than the NRT values because NRT is only considering proportional fair value. If you multiply any value with this proportional value, definitely the value will be bigger. So RT services definitely will have higher K value than NRT services. So RT services will be scheduled first compared to NRT services. One last algorithm with which we'll finish off this. That is this. Token queues mechanism. What is this? Instead of counting each packet, how much time it's waiting in the buffer, you kind of, based on whatever is the promised data rate for any particular flow, you kind of allow some virtual tokens to enter into a token queue. For example, if there is some amount of promised guaranteed bitrate applicable for a subscriber, for that particular guaranteed bitrate, at what rate the tokens can come into the flow, token bucket, you decide that RI flow. If your data rate is higher, you can send tokens, imaginary tokens into the bucket at a much faster rate. You can send 10 tokens per millisecond if your data rate is high. If your data rate is low, you can send only 5 tokens per millisecond. It is like that. I'm just telling you 5 and 10 relatively, just an example. If your data rate is increasing more and more, your rate is increasing, your rate of sending the tokens into this virtual token queue will be more. Now, instead of considering your packet delay, you will consider something called as a token delay here. Token delay is defined as V of t, which is queue length. How many tokens are present in your queue, in your flow queue, versus what is your rate. Ri of t is telling you the rate of generation of that queue. For example, if you are sending more and more packets, you will pull more and more tokens because to send every packet out, you have to get your data scheduled, packet scheduled, you have to pull a token, you have to remove a token from the token bucket. Whenever every time you remove a token, the bucket size will be reducing. If bucket size is reducing, this queue of time will be reducing. If it gets reduced, if your VA of t, which is your waiting measure, will reduce. If your VA of t is reducing, that means you will have less chances for your data to be scheduled. So that means the more and more tokens you pull, your probability will be reducing, your priority will be reducing because your VA of t will be reducing. This VA of t will be considered as your waiting time or your your wait value to decide whether to allocate the resources for you or not. So that means you kind of sending less number of packets. You have promised one data rate, but you are sending less number of packets. You are not sending at the same rate as your promised data rate. Then your number of tokens will be increasing in the bucket. If the number of tokens are increasing, QI of t, this value will be increasing. When this value increases, VA of t will be increased. If your VA of t increases, your scheduling probability will be high. So the idea of this token queue is what is the promised data rate for you, and out of that, how much you are utilizing. It kind of derives that mechanism. What is promised for you is tokens. How many you are pulling and scheduling your data and sending it out? That is your data rate. If you pull everything, next time you will be given less priority because Q of I becomes 0. When there are no tokens, you are not allowed to send. How much time your packet is getting delayed in your buffer, you will how many tokens are present based on your promised data rate versus what is the incoming token rate. You will take that value, you will consider that as your measuring criteria for deciding whether the data to be scheduled or not. That means if you take multiple subscribers, this is one subscriber. If you take one other subscriber, he has got only 4 tokens. Now, out of these 2 guys, whose possibility for scheduling is high, definitely this guy has got more chances for getting its data scheduled because he's got more tokens, VI value will be high. This VI will be used in place of the previous 2 algorithms that we have introduced. So, in place of actual W of T, earlier we have studied actual delay. In place of the actual delay, in the previous 2 algorithms we have studied, you are replacing it with V of T, VI of T, which is your virtual token delay. If your virtual token delay is more, that means more tokens are pending for you. That means you are sending less data than your promised data rate. You will be given more priority. That too by considering your channel conditions. This is your proportional fair algorithm to consider your channel conditions. So that means everybody's GBR will play a role in this token mechanism to determine the token generating rate, token generation rate, or we call it as RI. It will identify RI. And if the queue size is increasing, your VI of T will increase. If VI of T increases, your K value will increase. So you will have more chances for resources to be scheduled for you. Is it clear for you guys? Understood? Token queue? Any questions? Have you all understood the token queue? Because this is very widely used algorithm. Of course, you guys have to implement this. Hello? Yeah, if your guaranteed bit rate is high, you can generate more tokens. So your queue will be increasing. If queue increases, you will have more priority. If your queue is decreasing rapidly because you are generating the data at the more rate than your promised rate, your guaranteed bit rate, then number of tokens will be reduced. When number of tokens are reduced, length will reduce. So when you compare length versus your rate, which will have a lower value, because your rate is constant, but your number of QI of T is reduced. Number of tokens are reduced in the token bucket because you are sending more number of packets than your guaranteed bit rate. So automatically your scheduling possibilities will decrease. So this token bucket is a very important mechanism to exactly provide the promised quality of service or the guaranteed bit rate for the subscribers. Are there
PBR, prioritized bit rate for the subscribers, in a bucket size duration, in a BSD. Of course, not only that the token value is important. Now you take a look at the next one. So we have even the probability. If there is the high probability for the time violation for a guaranteed bit rate, AI is indicating that, then you will have bigger value in K if the probability of violation is increasing. So how near you are for your actual packet dispatching? Because we have the BSD, which is a monitor. Every BSD we have to send PBR, especially in case of guaranteed bit rate services. So AI will be will be computing that. What is the probability for this window to be failure, BSD window to be a failure? It will derive the higher K value or lower K value. For example, just now you have dispatched the data. You still have another 200 milliseconds to dispatch your data. So definitely theta value, the probability will be very low because there are 200 milliseconds means there are 400 TTIs, 400 transmission time opportunities. You can schedule the resources for this guy any time in these 400 times, any one time. You can allocate the resources and send the data. So there is no probability for failure. Probability will be near zero. When this probability is near zero, K value will be near zero. So obviously that guy's data will not be given priority over other guys. Other guys where K values will be higher, you will give more priority to the other users whose A value is reporting higher probability for failure or whose BSD values are fast approaching. Okay. If you have any questions, you can ask. Otherwise, that is the end of today's session. Anyone have any questions? Have you understood the scheduling algorithms, guys? It's important for L2 guys. Understanding the basics of it at least. L2 team.